Hi everyone, this is a new laboratory video about the slotted line. This video is being done during the COVID-19 time, so it's a little different in that I'm going to show you how to collect the data and then have you analyze the data I collect since you can't be here to do it. The lab handout's kind of long, but it's got a lot of pictures in it, and I wanted to be able to show you, since you're not here, some of the samples we have, and so you could have a better feeling by watching the video and analyzing data. So, my pardon if it is too long. So a few weeks ago we did this laboratory where we connected a generator to this LC transmission line. We put a load on the end and we measured all of the voltage points along the line. Right? There were 18 sections in there, and we set it up so that each section was equivalent to 10 degrees. We could do that because we had control of the frequency there. And then we saw how a pattern or voltage pattern was created associated with the transmission line. And it was to illustrate the reflections from the load. So we're basically going to do the same thing, but we're going to do it at RF frequencies and with a couple twists. So the handout talks about several developments of this technique over the years. It starts out and it talks about what we call the perforated line. And this is a perforated line. And what we mean by perforated is you can see it's a coaxial line. That's an end connector there. And there are holes drilled into the outside conductor. And that would allow us to go and probe these individual points. This, an older unit, has spacing of 1 inch per point, similar to one L or C network there. But this is the distributed line, meaning the L and C are in the transmission line, not as discrete components, but microhenries per meter or per inch or whatever, and capacitance. This line is no longer used, right? It's been obsoleted quite a while ago. But what they did instead was they created this unit called a slotted line, right? This is a slotted coaxial line, pretty old also. You have a transmission line connection on this end. You can put any kind of load, you can adjust the carriage or the measurement point. Now, the reason why we call it a slotted line is if I tip it over, you can actually see the slot cut into the coax. That little slot goes the full length of this line, or near the full length. And then there's a probe that is connected to one of these connectors, and that goes down in to measure the RF signal. There's a lot more about that in the handout. You can read about that. The second port here was for tuning for the probe. This unit has also been obsoleted for a number of years, but it was replaced by a very reliable unit called from Hewlett-Packard, who is the world's leader in this business. And so we'll use this unit. Now this is also a slotted system, but it's very different. I'm going to turn it on the side. You can see the center conductor down in that channel. Right? This is about 3/4 of an inch, it looks like there in that slot. That is the center conductor down in there. This is a special form of transmission line we call a slab line because it has 2 ground planes on either side and then the center conductor. Now, what we do is we put this unit, which is the same as the probe, This is what it looks like when you take it apart, right? There's the probe. You can kind of see that. Let me adjust this a little bit. There's the probe that goes down into the area near the center conductor. That probe acts a little bit like an antenna to detect the electric signal, field signal down in the channel. That signal is brought out to a connector, right, and we measure the signal. There's a few other parts to this. This large knob on top is a tuning knob. When you read the handout, you'll see that this is equivalent to an LC parallel circuit, and we'll use that knob to tune for the given frequency. This unit had to be tuned for a specific frequency. This little knob here is actually adjusting the depth of the probe. So we don't want to get the probe too close to the center conductor, certainly don't want to touch it, and so by adjusting the probe depth you could adjust for sensitivity or low signal level. And then we just move this along, and then we can measure, and we have a metric scale here. This is each 10 is 10 millimeters, so each mark is a millimeter, and then we have a vernier scale, which if you don't know how to read a vernier scale, it gives you one more digit of accuracy there. So this unit is basically accurate to 0.1 millimeters. Very fine resolution. This unit could be used up to over 4 gigahertz. Right? So we're going to connect loads to this and a source on this side. Look at that setup with all the equipment together. So here is the main section of the measurement of the lab. Please read the other material so you'll be able to better understand it. But there's 3 main components in the setup: the source, the slotted line, and the VSWR meter. So we talked about the slotted line. I've hooked up a coaxial unit up to the slotted line instrument, or the SWR meter. SWR, VSWR is the same thing in this case. We set this on high. That's just a setting for the diode. And then we put this on the normal position. And then this is a variable amplifier that we'll use, or gains adjustment. Now the unit, the source, let me turn off the source and I'll turn it back on to show you how to set it up. So we turn on the source. This is what we call a microwave sweeper. It can sweep through various frequencies, which is useful for us to test lots of devices. But in this case, we're going to use it on single frequency. The default there is halfway, which is 655 megahertz. We're going to put it on 833.33 megahertz. And I explain why I like that frequency. Turns out to have a wavelength of 0.36 meters, so every millimeter is essentially 1 degree. We have to turn on this square wave modulation because we have to modulate the signal that goes into the slotted line. On the slotted line, we come out from the generator. Okay, the generator's off right now, the RF is. It comes through a cable. I have put an attenuator, which is just a signal reduction device here, and that's mostly to protect the generator. If I had an open circuit, I could reflect back a signal into the load, into the generator. So this is an old thing we used to do to protect our generators. Not quite as necessary as that. But we do get a reflection if we have an open. So after the attenuator or pad, right, we have the slotted line. Slotted lines, by the way, can be used either direction. This could be the source side, this could be the load side, but it doesn't matter. All right, so I've got an open circuit here, right? And I've set it up for 833 megahertz. In this case, I've got a signal on the generator, and I'm going to adjust this tuning knob. And we're going to adjust it till we get the maximum signal, which is should be to the right direction. So you have to move the probe. You got to move the carriage to find the maximum signal. So as I move this along, it's a lower signal. I'm going to downrange here. See if I could see it a little bit better. Oh, there it's moving a little bit there. Let me retune the unit. A lot of manual tuning here. There, we got it. So that's the tuning of that bandpass filter to be exact maximum. But you want to find a maximum, and then you're going to slide the scale again. That's to make sure you're on the maximum. So as I go one direction, it goes down. When I go the other direction, it goes up and then down. So I want to find that peak. And then I'm going to set that, use this gain to set that to be maximum value on that scale. VSWR in this case is measured from the maximum to the minimum. So first we set the maximum up there at the 0 point, or if you look closely on the VSWR scale, that's the 1.0 VSWR scale. So that would be 1 to 1. Now, the output of this VSWR meter is I have brought it over to a digital voltmeter, and the digital voltmeter just reads a DC value out of the VSWR meter. And it turns out 1 volt is about full scale on this meter, this analog meter. It's a little over full scale, but we'll adjust that back down a little bit to 1.0. This is just a gain amplifier adjustment. Everything, all of our measurements are going to be relative. Now what we're going to do is we're going to write down the position of the probe, the condition of the load, which in this case was an open, and then we're going to record the voltage values, and then you're going to plot those. So I'll include that data. After we've done that measurement, so you can see I have a reading, I'll move it to a certain position, and normally I just use the numbers on here, 200, 210, 220, and take my measurements. I do try and find the peak and the null. You can see as I move the carriage, it goes through a range of values. Of course, for an open, the VSWR is maximum. So if you look at our VSWR scale, this one is the one we're using right here. It's going from 1 to more than 4. Of course, with an open, it will be infinite. So I've gone back to the peak, and now I'm going to insert the match or 50 ohm load on the system. Now what you'll see when I insert the 50 ohm is the signal dropped. And you say, well, it's a match, that's a better system. But remember, we're measuring, this meter is measuring reflections. And there's more of a reflection for a mismatch than there is for a match. And in fact, if I move the carriage now, you'll see the needle is barely moving, right? So that means the system is very well matched, because there's the difference between the maximum and minimum is almost the same. In fact, if I dial this up and go to the top VSWR scale, I can set the resolution a little finer even. Okay, I got a little variation on this meter, but I'm going to expand the scale so I can read the VSWR. And you'll see, okay, so I'm going to move the carriage here. So VSWR is basically 1. It's varying a little bit. The top scale, you can see, I'll zoom in and you can see that's a VSWR of 1.05 and it's staying less than that. 1.05 is equivalent to 50 times 1.05. Or very close to a match. So this is the sample type data you'll have in the data file. So we're going to record the data position, where on the slotted line. Finally, the DMM voltage, which comes from this unit, which is essentially the same as the VSWR meter, but this is in linear volts and this is in VSWR reading. Then I'm going to go back and find the minimums and the maximums, the peaks and the nulls, and then we can do some wavelength calculations related to those. All right, so that's the measurements that we're going to make. I'll give you data for a match, for an open, a short, 100 ohm, 200 ohm, and I'll try and make 25 ohms. And then your job is to plot the data and comment on the data. The idea, this is how data might look. This happened to be for a short. The short was someplace out here, because you can't measure right at the short or the load because there's a connector, so you won't be able to measure that exactly at the end of the line. This is what the Wikipedia version looks like, so you can see that those two match up pretty well. All right, good luck. Send me questions if you have them.